All right, so generally speaking, I just wanted to run over the following. So give you an overview of what it looks like, how you can access the resources for people who are just getting started, um, how you run various pieces of software, and then we'll talk about the probably everybody's least favorite part is dealing with Slurm, um, and just talk about the resources that are available in terms of that. Okay, so let me just first talk about what we're trying to accomplish here. What we tend to talk about this in terms of Einstein's academic research computing system. So academic research as opposed to the hospital's clinical medicine. So um, we don't run things like a hospital would run things. We run things specifically around academic research, and try to give people as much access to anything that they need as possible. So we try to put together and keep our systems up to date. Some of you folks may have been around long enough to know that, due to various concerns of, budget and everything else in the past, sometimes it's been a bit rocky. So we have tried to keep things on a much more uh, even keel, get all the software up to date, refresh all the hardware, and that also includes in the storage side of things. So there's been a lot of work on the storage as well as the compute cluster. And this also includes, we don't run people's lab systems, but if you have questions about how to access things, what's the best way to do things, we're always very willing to talk to you about getting everything from getting data off of your instruments and how to then analyze that data to just issues you may have with networking or anything else, right? I mean, if you don't know where else to start, you can always contact me and I can put you in the right direction. Okay, so very broad overview. Those of you who have already logged into the cluster at some point will have seen the way that things are organized is in terms of the Slurm batch scheduler. And the reason for this is that there's, roughly about 100 compute nodes. We want to make sure that everyone has access to these, that they're used as much as they can possibly be used. But at the same time, we want to make sure that if somebody has a high priority project that needs to get through, that they can, find space on the system. So we try to balance that out. And this is done by these, what are called Slurm partitions. You may think of these as queues. Officially, the way Slurm talks about it is these are partitions, and each partition has its own queue. And we basically break this up in terms of how long something is going to take, right? So um, you might understand we don't want the entire system to be taken up by people who have jobs that are going to run for 2 or 3 days or weeks or whatever, right? So we need to have room for people that just need to get something done quickly. So we have, everything from a test queue, which is for design really for people who just want to run some script to make sure everything's working. We have, quick queue. We have a high throughput queue, which is designed for people who want to, put like 10,000 jobs in the queue. Obviously, they're not all going to run at once, but it will just process them through. So, that's what the high throughput thing is for. Normal queue is just like this is a typical one that people would use. Unlimited means you can request all the time and all the memory you want. We do have 2 large memory servers, which have about a terabyte. We're hoping to get some that have even more than that sometime here in the future, but that's what we have right now. And then we have a number of GPU servers, which all have NVIDIA A100 GPUs in them. And so those are all what's part of the cluster. We also have, as I'm sure you've interacted with, the login nodes, which are just designed as very lightweight, kind of like, what your laptop laptop would do, maybe even not as much as your laptop does, depending on what you have. All right, and this just gives you a picture of what this all looks like, right? So um, on campus, we have the physical machines, we have the physical network. There's a network which goes to the cluster to everything else, and then there's the campus network. The campus network then has a firewall in which we have a great deal of security, which you'd appreciate. And then if you haven't already found out about it, in the past there was Montefiore had maintained a very old VPN system. We're not using that VPN anymore. We're using something called Global Protect, which is a portal which allows you to basically log in from outside, which is what I'm using right now. And we also have, for sharing data with other people off campus, besides something like Dropbox, we also have this thing called Aspera, which some of you may have worked with, and Globus, which probably a number of you have worked with as well. We also have ways of dealing with Amazon, AWS, Google, all those other, standard tools. But this gives you, general idea what the whole thing looks like. The storage down here, we refer as data.einstein. And then, like I say, you all have these cloud workstations, and then we have this other interface, which is called cluster.einstein, which is a web GUI, which at the moment mostly just deals with certain interactive workloads, but we'll talk more about that later. All right, and the other thing is if you need help, there's a couple of different places. First of all, you can always put in a support ticket. This is very useful because we make sure it gets to the right person, and then that person basically has a record of which both you and they can see of what's going on. We have a couple different websites. This one up here is fairly new. We put up the second one here goes to the SharePoint website. I didn't try to type it all out here because it's a huge thing. All of these slides will be available later, so we'll put them up on the main website. All of these you can get to if you just go to it.einsteinmed and type down under HPC, you'll find all of this information. And one other thing I'll point out is we're starting to collect if people have examples of scripts or something that you want to share with the community. Within it, there's a thing called /public, and under that, we have this thing called Code Lab. So I'll talk a little bit more about that later. So, like I say, you can always go to this to support and put in a request there. And if you go to, here's the full address if anyone wants to. Hopefully all you guys have this bookmarked already. If not, and you don't remember what it is, just send me an email and I will point it to you. But at the very top of the page, we have a whole bunch of white papers and a few videos and so forth on how to do various things like MATLAB, Schrodinger, how to use the Slurm scheduler, and so forth. We always appreciate feedback on these. So if, I just kind of put things together, what made sense to me. So, again, okay. So what you need, we're going to go through this. So how do you get onto the resources? How do you connect to the system? And one thing which people may be less familiar with is the various ways to manage your data. So we make the system available clearly to anyone who's an employee or student here. We also can accommodate people who have collaborators who are not part of Einstein. It's a bit of a process given that they have to get credentials from Montefiore. So there's two different systems that's worth talking about. So one is the storage itself. So anyone can get access to our data lake, the storage data at Einstein. You don't have to be someone doing computation. So if you just have a whole bunch of data you need to store somewhere, or not, you just need storage, and you want to keep it in a central place, you can get a storage account. It's no charge to do this, and we will go over more about the data storage later. Separately from that, but connected, is if you want to use the HPC systems, you will then be given a what we call a login node. This login node actually is 2 cores, 4 GB of memory. It's just mostly designed so you can log onto the system, see what's going on, write scripts, maybe run a little Python, things like that. It's not very powerful. Anything that you want to do that requires a lot of work will go onto the compute nodes themselves. If you're on campus, you can either use SSH, or you can just type this, whatever your username is. So like IBB Hammond, HPC I7 Medu in your browser, and you'll be taken to your login node. So hopefully that's old news to most of you. If you're off campus, you need to get access through Global Connect. And if you don't already have that and you want it, just go to the support site, say, please give me Global Connect, and we'll go from there. If you haven't already used Global Connect, this is what it looks like. There's a piece of software you need to download onto your local computer. It will then give you a screen that looks like this. And we have complete little document of how to do all this available for anyone who's wondering how to do it. It works pretty well. I've been using it now for several months, and it seems to be a much more robust solution than the one we used to have. Okay. And then, as we talked about before, so you can go directly to your login node. We also have this thing called Clustered Einstein Med. It's particularly useful. So if you've used the cluster, you notice that login nodes do not have any way to do exporting. So if you want to run MATLAB on a login node, you can do that through a command line. But if you wanted to actually run the MATLAB user interface, there's no good way to do that through just through Slurm. So we've set this up through this website, cluster.einsteinmed.edu. You can run MATLAB, Schrodinger, Jupyter Notebook, RStudio. You can also just bring up a something that looks like a desktop, but it's actually would then be running on a compute node, and each compute node has 50 cores and 300 GB of memory. So you can use it interactively in that way. This interface actually has more capabilities than this, and we'll, over time talk about that some more. Okay, so if you haven't already used this, I'll go by this real quickly, but this is what it looks like when you log in. You'll get this screen. The one thing I'll say, if you haven't already done this, is there's 2 levels to log into. The first one is you have to log into the cloud workstation, and then second, you have to log into Linux. Now, after you do this the first time, if you don't log out of Linux, then you don't need to log back into it. But it can be confusing when you just get a black screen that doesn't look like anything. You just need to hit return until the Linux prompt comes up. And again, we have a white paper on how to do this. Okay, so something that people may be less familiar with is all the different ways you can manage your data. So like I said, we have a large data lake called just data.einstein. Some of you may have been here when we moved the entire infrastructure off of our old equipment onto our new equipment. And during that move, we had to have data.einstein and data2.einstein. The two is no longer necessary. It will take you to the same place. So data.einsteinmed.edu is the same thing as data2. You don't really need the two anymore. So that is basically everything down here at the bottom. So it's a very robust system. It's has very high performance connections to the HPC cluster through this private fiber backbone. But in addition to that, we also have ways that you can share, either using Globus or Aspera. These are very simple tools. You just have to get set up, and we can help you with getting those set up. You can also access lab archives. So if you want to put stuff up there, and we're currently working on a contract with Figshare to be able to put your data up in Figshare, get object IDs from Figshare, and share these all out with your publications. And Figshare has a lot of capabilities with respect to that. So if the NIH, as you know, you have to have a data policy. So these all are parts of potentially that to make this findable, accessible, interoperable, reproducible, all that good stuff. I won't just go through here and read all of this, but like I say, later you can look at it. The main feature that we have is, first of all your data can reside in data.einstein. You can get at data.einstein from your lab computers, from your laptop, from anywhere. You can either mount it in Windows or on a Mac. You don't have to mount it, though. You can see it through your file browser as well, depending on whether you're on a PC or a Mac, just because the way that the different ways that they work. And if anybody's been around long enough, to remember before we went over, we had a system that was getting very old. It was a little bit not so reliable sometimes, but the new system is all your data is stored physically in two different places instantly. They are in high availability, which means if one site was to fail, the other site just keeps going. We've tested this out. It works really well. In addition to that, then all that data is then in snapshots, which means so once a day it takes a snapshot of everything, and then it also backs up everything to tape. So, and then after that's all done, we then store everything in a third site for disaster recovery, just in case the entire campus went down and we lost all power and everything else. So we save everything off campus to a repository, and that way, like I say, we have good resilience. But also, if we lose power to one building or if there's any other issue, this thing will just keep going and going. It's also based on a very advanced file system, which protects against things like bit rot, if you're familiar with that term. We don't delete things off of this file system. So unless you delete it, we certainly don't. So we've got files that are 10 years old easily sitting around on the file system. This is obviously a concern for people with NIH grants or something where they require you to keep the data on for very long periods of time. So again, and we can also set up, and many of you have, lab folders so that you can share data within the lab. Everything is set up around the security so that only certain people can see these things. So as you've probably noticed, like you can't see somebody else's home directories unless they specifically give you permission to do that. The only way to do that is to submit a ticket to us. So the other thing I also say on the security side is if you are going to be dealing with patient identifiable information or PHI or any other sensitive information, it should not be on this file system. We have a separate file system set up specifically to do that, and it is highly regulated. So that's very important. If you have any questions about whether your data is going to be an issue, but we don't want anything that running around with patient names in it, anything like that. That's not what this file system is about. And again, if you accidentally delete something or can't find it, just send us a support request, and if it's been backed up, we can restore it. Now the backups are done once a day, so if you created a file and deleted it by accident all in one day, we may not be able to get it back. So, okay. I'm not going to go into this too much, but if you need to access data from off campus, or if you have a collaborator that wants to access data, or in the case of Globus is also very useful for just moving data around campus. If you have like very large files that you want to move and you want to make sure that they've completed, and you don't want to try, just dealing with copy and paste. Globus works really well for that. It takes a little bit of setup, and our engineers can help you get that set up. Aspera, Fastspec, and shares, some of you have dealt with in the past. Fastspec is a email-like system where you can basically just email a link to somebody and they will have access to that data for a certain amount of time. Shares is more like a Dropbox where you send a link and they go to and they can see everything that's in that folder. Okay, so let's talk about some of the things that just came up. So in terms of running something on the system, there's several different possibilities for how you do this. And I just want to make sure people know, because in the past this wasn't always the case, but if you have an application that does not need root privilege to install, which means it doesn't have to install any weird libraries or anything like that, you can do this under your own account, right? So there's tons and tons of scientific applications. You can just download them and run them, and that's not a problem. If you let me just say, we have all the common compilers that people might want to use. If we need to add something, we're happy to do that. Just make sure you're going to compile something that you're familiar with how to do that. If not, as you know, we're willing to do that. So typically, when somebody asks us to put on some things, we do one of two things. The first one would be to use Linux modules, these environment modules. What they do is when you invoke them, it sets up all the environment variables necessary to run whatever it is. So like right now we have R set up, many different versions. You would then go and use module load. If anyone's not familiar with that, I can run through that on my account and just show you a demo if anyone's not familiar with that. But it's pretty straightforward. And so if you put in a request and say, hey, I want XYZ put on it, this would probably be the first way we'd look at it. However, the other common way of doing this would be through Conda. And there's some other things that are like Conda now that are getting popular as well. The nice thing about Conda is, again, you can do this yourself. You don't necessarily need us to do this. If it's an application that like your entire group uses or large numbers of people use, we're happy to set it up as a shared Conda library. The only downside of the shared Conda libraries is it's owned by root, so you can't just change it. So if you're someone who, like especially with um, AI and DL and so forth, a lot of times these things are changing constantly. There's new versions of this, or you want to do that. So if you're familiar with using Conda, you can do that locally from your own account, and it's not a problem. You're welcome to do anything you can do in Conda. I should also mention we do have ways of running containers, Docker containers, and other containers. It's a little more complicated, but uh, it can be done um, if you end up having these containers. Docker containers are a little problematic because they require root access, so we have to go through some special magic to get that to work. So, I mean, those are the main things, and they're great in terms of that they're self-service, right? Especially with Conda, it's typically very easy. Sometimes it can get a little crazy, but usually it's very simple. Okay, and then the other part, which I'll show here, is this cluster.einstein. And like I say, it has a lot of capabilities, but one of the main capabilities is we're able to run graphics user interfaces through it. And if I can get it to, it doesn't want to do that. All right. Let's see how do I get out of, there we go. All right, so let's bring this back up. Okay, so just real quick here, if you do module avail, you'll see like lots of things you can use. If you have any questions on how to use that, I have again, we have little how-to papers on almost all this stuff, and you can do the same thing with Conda. If you want to see what your current Conda environment is, you do Conda list. If you do Conda list and it tells you you don't have Conda, then we just need to make sure that you get it set up because Conda needs to be initialized. Okay. So now cluster.einstein is a little bit different situation. So when you first log into it, it will look something like this. Up here, we have things to tell you about your account. The main thing here is the marketplace. This thing is organized in terms of the marketplace. So this is the big potential of this tool is in fact these workflows. You can create your own workflow if you are pretty good with Python, and there's this Python package called Parcel, which is what all this stuff is written in. So it's a bunch of Python that tells it to do this and do that. Generally speaking, I don't anticipate too many people are going to go that far, but it is possible to set up workflows to do a lot of different things. In our case, right now, we have things like Jupyter and MATLAB, um, the Schrodinger tool, RStudio, because those all require um, the exporting so you can see the GUIs. But potentially, we could set up a web interface to any application you wanted. And I'd love to find somebody who has something that they feel like they wanted to automate. So rather than going and creating a script yourself, you can go fill out a form online. This is my input file. This is where I want my output file to go. Click go, and it'll go run, I don't know, Blast or something, whatever it is you want it to do. So this is where you find the workflows initially. You click on the workflow, and it will then show up over here. And then you just click on one of these workflows and you fill out a form. And basically what it does, and I'll show that. But the end result, though, is here is MATLAB running on compute node 760, and it is running MATLAB. You can run RStudio the same way. You can run Schrodinger Maestro the same way. You can, in fact, just bring up this desktop as well, right? So, I mean, this is the same desktop you see everywhere else, and you can do everything here you want to do. So if you just needed a really big workstation, this is one way to do that. The only downside, of course, is once your session ends, all the stuff in here will disappear, right? So, and that's fine. Just make sure to save your work. So what I'm going to do here is I'm just going to end this and show you how we started it. So I'm just going to cancel this run. And I think somebody had a question about Jupyter Notebook. So let's do Jupyter Notebook. So first of all, so some key things. You'll see down here at the bottom, it says my compute resource. This is bright green, and it should show one. If you've been using it, like I have, it could show 2 or more. It just depends on how many sessions you have running. If it isn't bright green, if it's like kind of like dull green or anything else, or over here, it'll say active. If it's under requested or stopped, you need to come press this button and get it running. And if you can't do that, for some reason it's being difficult, you can go back up to the top here, click on account. You click on restart workspace. I'm not going to do that right now because it takes time. You restart your workspace, you sign out, you sign back in, and then try it again and it could work. If all that doesn't work for some reason, then please contact us and we'll have one of the engineers take a look at it and give it a kick. Okay, so if you click on Jupyter, it's going to give you this form. The main things that really matter here are how long do you want this to run for, which going to determine which queue you want it in, or do you need a GPU, right? So if you're doing TensorFlow, for example, you will want a GPU. And in this case, it's just going to use one CPU for a task. If I need a lot of memory, I can tell it I need 20 gigabytes instead of the default. And if I'm going to be running for a long time, and I'm going to be running this interactively, of course, you can use Python. If you have a Python script that's going to run for 5 days or something, just run it through Python. But again, if you're trying to use Jupyter Notebook and let's say you want to use it all day and you don't want to worry about being logged out, you just tell it, okay, I'm going to be working for the next 8 hours, right? Whatever. You hit execute. You should get this little thing that pops up. It's going to do it. So right now it's doing a lot of work in the background. So I should just say everything that's happening here, it is not your login node, right? This is a different system. It can access your login node, but it's not working through your login node. Okay, so down at the bottom, it's going to start showing you what it's doing right now. It's basically thinking. Okay, there it goes. It's going to spit out a bunch of stuff that you don't really care about. And then you can see it created a job. So if you go and look at the job queue through Slurm, you'll see I have a job. And now it's setting other stuff up. And this little thing came up at the top here. It says that you have an interactive workflow. So you can just miss that and click on this little eyeball thing here. It's a little bit different than the way it worked when we first installed it. So if you are wondering about that, yeah, sure what that's doing. Okay. So now Jupyter is a little bit different than the MATLAB one, is it doesn't just pop up a window. It goes here and asks, gives you a file browser for your Jupyter notebook. So this file system that you're seeing here are your files in the cluster. The only difference is by default, it puts everything under this PW directory. So this thing called storage, which I'm looking at, got a lot of broken links. My goodness, I got to clean that up. So there's all of these different things. So if you're wondering, is this the same thing? Yeah, from a storage point of view, it is looking at the same thing. So if I double click on that, I have some little things that I created here. If I just click on this, then it creates another tab. And there it is. Now, one thing to look at is it has these things it calls them kernels, but it's basically a conda environment. And if you have your own conda environments, like I have one for Gaussian, it shows up here. I don't need it for this, but so in this case, we have different conda environments. And if you want to create a conda environment for this, there's a couple of special commands that you need to use there's some packages that need to be in the conda environment for it to work properly. So if you have any questions about that. In this case, I just tell it, okay, I want to use this as my kernel, and just tell it to run the cell and sit there for a second and tell me, okay, I'm on GPU 103, and then you can go down and put in your code. This is really bad code because it doesn't work and it gives me a bunch of information, but I wasn't really concerned about doing work. I just wanted to get something to see what it would do. And then when you're done, you can save your work to whatever, log out. If you don't log out, you can just kill it and it won't save anything. So, and at that point, you come back here, you could start something else differently, or you can just, if you go back to workflow or back to the home directory, you can then kill it whenever you're done. Okay. Everything else I have is just about using Slurm, which is, I'm sure, everybody's favorite topic. So I will say, whoops, I went and did that again. There. So I will say, if you are having issues with writing batch scripts and something, again, feel free to contact us, put in a support ticket. Our engineers are happy to talk to you about this. They don't know anything about your application, what it does, but in terms of calling your application, they can certainly help out. And I'm happy to help as well. And like I say, in some cases, we may actually find better ways to do something. But basically, we're just going to run over what it is. For a lot of your applications, once you get a basic script running, you never need to touch this thing again, except, change input parameters or something like that. Okay. So first of all, what is the thing doing? And if anyone is wondering where they got the name from, yes, in fact, they were Futurama people, but they figured out how to make it a nice acronym. So it allocates the resources on the system, right? This is so everybody plays nice on the system. that, whatever resources you need. And the key in terms of the resources is principally time and memory. So um, we have certain defaults set for each one of the batch partitions. If you don't tell it otherwise, it will use the default, which are usually smaller than you want. So you need to tell it how much time you want and how much memory. Uh, and then you should be able to run without any issues. Um, if you're not sure how much memory you need and how much time you need, um, you can, do a little bit of trial and error is good. You can just give it a really big number and see what happens. Um, Usually after you've run something a few times, you start getting a good idea. Um, the key thing in terms of just how you set these things is that whatever you ask for, Slurm is going to try to get for you. So if I ask for 50 cores, which is all the cores in one system, it is going to wait until an entire system is ready. On the other hand, if I know my package only uses one core, then just request one and you'll get in very quickly. And the same thing with memory and time, right? If there's, uh, if you can keep the resources as well defined as possible, you're going to get in and out quickly. Um, each one of these partitions only has a certain number of slots. The unlimited queue, which is for people who want to run forever, basically, has the smallest number of slots. So again, if you don't really need to use that, the normal queue, the one above that, you can run for 2 days. And we set it to 2 days because we've noticed that most everybody's jobs doesn't take more than, one day. Most of the jobs are, 16 hours or something, right? Whatever it is. Um, we do keep an eye on this and try to make sure that nobody has to wait around unnecessarily. But sometimes the system does get busy and we do have to pay attention to this. So just a quick note, how does this thing actually work, right? So Slurm has these things called partitions. Each one has a queue associated with it. In our case, these queues, they don't map onto specific pieces of hardware. They map onto pools of hardware. And what it's going to do is partition A and partition B. Partition A has a certain number of queues. B has a certain number of queues. It will go through and, if there's a node, it will put my job and your job all in the same node. And try to, optimize where all these blobs go so that everybody gets things done as quickly as possible. So it's kind of like Legos or something. Um, this is also on that SharePoint website. And this is subject to change over time as we get new resources or sometimes, the needs change. But generally speaking, like I say, we have the test queue, which has a limit of 1 hour. All of these in default to having one core, so Slurm calls them CPUs. So they're used interchangeably as far as Slurm is concerned. So if you want more than one, you need to tell it. The default time limit, the test queue is 10 minutes. So if you need 1 hour, you need to tell it I want an hour. Same thing with the quick queue, is limited to 4 hours. Again, it's just designed to give it. These two queues together actually have a couple of servers that are assigned to them so that no matter how busy the system gets, if somebody needs to just run a 10-minute job, they can get a 10-minute job to run through here. Now, the place that this is different is high throughput queue. You can queue up. So there's a limit to how many things you can put in the queue so that, again, one person can't just queue up a bazillion jobs and nobody else gets into it. But for the high throughput queue, it's designed for somebody who wants to put in a very large number of jobs and just go home and let it work its way through. And this has been pretty successful. It basically only lets 1,000 jobs run at the same time, but you can put 15,000 jobs. And of course, this is the limit for everybody. One person isn't allowed to get all 1,000 of these slots. Normal queue, again, 2 days, 48 hours, but the default is 1 hour. So if you want to use more than 1 hour, make sure you tell it. And there's a memory default. Again, you can tell it whatever you want. The large memory queue here, they have 1 terabyte of memory. So if you need a lot of memory, everything else has about 300 gigabytes of memory, which, for most jobs is more than quite enough. And we have a GPU. These two queues are the same hardware. This one is just designed, again, kind of the same way the quick queue is we try to leave some space for somebody who just has a very short job. But a lot of times these GPU jobs can last for a long time, and so you just use the standard queue. Okay. Now, first of all, if you really want to do a deep dive into everything, there's this group called SCEDMD. They support Slurm. Slurm is open source, but SCEDMD provides support. We have a support contract with them so that if something's going wrong with it, we can go and find out from them get support. But they have extensive documentation on how to use all this stuff. They've just used things that are like the most popular and most required. So there's 2 commands that you'll deal with most of the time. SBatch is if you want to submit a batch job, right? Just means that you just want it to run. Now, within that batch job, you can use srun if you want to. You don't really need to. What srun does within a batch job is it creates separate job steps. And those steps, when you go and look at it from the Slurm point of view, like if you ask about statistics on my job, it will identify each one of these separately. If you don't use srun, which I almost never do, but if you don't use it, it just thinks it's all just one long job, which is perfectly fine. srun by itself, however, allows you to log on to a node and do interactive command line work. Again, it won't let you bring up a GUI, but it will do command line work. So if you just want to try out a command, make sure it's working, or if you just want to run MATLAB on the command line, you can fire up MATLAB that way. And again, these are some of the basic things. -P, if you don't tell it what partition you want, it'll default to the quick queue, which is probably not what you want. You can tell it how many cores you want, how many nodes. Most people, you don't need to worry about this. You're just going to use 1 node, which is the default. But the time, the memory size, there's lots of different ways to specify memory. Simplest one is just to tell it the total memory that you want. If you need 8 gigabytes, if you need 100 gigabytes. But you can also tell it how much memory per CPU. So if you're doing multi-threaded and you just want to keep increasing it per CPU, you could do that. If you're going to use GPUs, it's very important to tell it the number of GPUs you want. Otherwise, it's going to assume you want all of them, and it will sit around and wait until they all become available, which is not great. And that's the way Slurm works. Then you can do things like change the job name, tell it where the output, and so forth. Here's the output from Slurm itself. It may or may not correspond to your application. Most applications route the output somewhere else. So, just a quick example. So up we have a bunch of Slurm options. In this case, I'm telling it I want the GPU partition. I'm going to call my job name MOL. I'm going to use this string here is going to be my standard output. This little %J here just means it's going to stick in the job number so that every time I run it, it's going to increment this. So they'll all have unique names. It won't write over them. I tell it how many nodes I want, how many tasks per node. This is the same as telling it how many cores you want or how many CPUs you want. So I tell it I want 15. I want 100 gigabytes of memory. And then there's some additional things. In this case, this one's telling it inherit my user environment. So one key thing when dealing with Slurm is to remember that it doesn't inherit your user environment. So anything you've done in your command line right now, it's not going to remember when it runs. It's going to run it as if you just logged in. So if you want to tell it to remember everything you just did, you need to tell it this, or you just need to put explicitly everything that you want to have happen in here. So for example, in this case, I'm going to use this program called Gaussian. If I had already loaded Gaussian, in fact, I'm using this user environment, it would know that Gaussian was already loaded, but I told it to do this anyway. And I got a bunch of stuff, and I tell it to run. In this case, the log, the output's going to call this thing called mol.log, right? So that's from the application. If I didn't tell it this, it would just go to the standard one. And then if you create a mess on the compute nodes, if you store files or something, please clean up after yourself. And the other thing is, some people are very clever and realize that anything you can put here, I can put on the command line. So if I create a bash script, which does several different steps, like I'm going to do some preconditioning, I'm going to, take my BAM file and do this, and then I'm going to do that, and then I'm going to do the next thing. I can create a script and then have it run sbatch and just put everything on the command line. And like I say, I have some very basic examples of specific things in the code lab area here. So someone's asking, is there a good way to estimate? There's not a lot of good ways to do it. The most straightforward way is to give it a lot of memory. First of all, if this is an application that you've run like on your laptop or something, that gives you some idea of how much memory it uses. You can look at it and see. I should just mention there are some things that you can do that are a little fussy, but you can do this. So for example, you can, if you run a job and it's running currently, you can go to the compute node that it's on, and you can run top, if you're familiar with top, on the node. So you could do this through srun. So I tell it test partition. Let's say I know that my thing is running on CPU 777, and then I have to tell it this nasty looking thing, pqi bash, that basically tells it I'm going to run the bash script. So this is what I use srun for most. So at this point, you're now logged on to this, and you can run top. And as you can see here, it gives you the memory. So right now, not much of anything's running on this, but if something was running here, you'd be able to see how much memory it's actually using. So that's one way to find out how much memory it uses. Now you just have to be careful because the memory changes over time. So if you look at it at the very beginning of the job and then later it uses 10 times more memory, so forth. So sometimes it's trial and error. Sometimes you tell the program how much you want, right? In the case of Gaussian, that's one of the input parameters. You tells it how much memory it gets to have, and it does it from there. So yeah, that's one issue that, again, it's important with GPUs to tell it, I want one GPU. In rare cases, you may want two GPUs or more. Most applications do not take advantage of multiple GPUs, but if you know for a fact it does, then make this whatever you need. At the moment, all of our GPUs are almost identical. We have a set of them that has a smaller amount of memory than the other set. I've only run it up against one person that actually that was an issue. So if you get occasional errors saying it ran out of memory on the GPU, then let me know and we'll let you know how to fix that up. Okay, and I talked a little bit about this, but again, it's important. Make sure you put the make sure you put in what you want, otherwise it will kill it. Remember that it is basically logging in as you, so it generally either will use the directory that you called it from or whatever. So, but you might just want to be as explicit as possible in telling it, okay, what directory it needs to be in and so forth. Also, Slurm does not necessarily run your bash RC. So if you have some really important stuff sitting in bash RC that needs to get run, you should probably source this. It actually runs your bash profile, which is a little bit differently. And this can sometimes cause trouble, especially with things like Conda. And sometimes for some people, the way that their bash RC and profile work, it interacts badly and it doesn't pick up Conda. So if you're having trouble seeing Conda, you can just source the conda.sh file that sits under the Conda, and it will fire up Conda for you. Okay. So after you've gotten past all of that and you want to see what it's doing, there's a couple of different commands. The most obvious one, or that for you is sque, sque. Now in my bash RC, I've made a lot of things to shorten some of these names. So if you do sq --me, it will show you my jobs. If you just run sq, it will send you a long list of everybody. You can also tell it you just want to see who's running in this partition. You can do other things. There's a lot of different commands here. There's another one called sinfo. Sinfo gives you more things about the nodes themselves. Again, you can look at it. It's usually not useful. Account will help you look at particularly like things you've already run. So if you do an account with your username or a job ID, it'll tell you what the status of that is in much more detail. And if it's already run, it will tell you when it ran and so forth. Another important one is cancel. So if you just fired something up and you're like, oh, I didn't really want to do that, you can cancel it. Or if it's taking too long, or if you're looking at the output and it's like, oh, this isn't working. So there's a number of these. Like I say, sq is the one you're most apt to use, especially if you tag on me. And that way you're just looking at what's my job doing? Is it done yet? So forth.